Alright, as promised, let's do a little more of that vector work with those vectors with multiple directions. Before I begin, let us go back over that tricky stuff, because that is immensely useful when it comes to vectors that go in multiple directions, angles, things like that. How do you know you're going to need trig stuff? You have angles. If you've got vectors that happen anything other than right on the x-axis or right on the y-axis, so completely horizontal or completely vertical, you're going to need trig stuff. Again, my favorite memory trick to remember the trig functions is SOHCAHTOA, and I separated it out this time so you could see the three pieces. So, first part, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. TOA, tangent, is opposite over adjacent. The nice thing about this particular mnemonic is the fact that it allows your angle to be anywhere in this triangle. When you look at just your sine function as y over h or cosine as x over h, that requires your angle to always be in this lower left or on this lower side of your triangle, so that x is horizontal and y is vertical. By doing it this way, that means your adjacent side is just whatever side is adjacent to your angle. So if they gave you this angle up here instead, suddenly this becomes the adjacent side. And without having to flip x and y in your brain, it still allows you to carry out the same trig functions. So I have long used this. I love it. I hope it will help you, because it has been invaluable to me. And I am not a math person. I will be the first person to admit that. Okay. So, this is the exact same problem that was shown on the last video, and we want to find the resultant. Find the resultant, translation, add them. But, since we have two angles, both of these vectors have x components and y components, means I can't just smash them together. If I want to draw them visually and try to get an idea about where my vector is going to end up being, we need to put them tail to tail and finish the box, quote unquote. So that means we're going to take this guy here. He's at 45 degrees, looks about like that. And my other one's at that 45 degrees and looks like that. Then we create our mirror images. Needs to be a little bit taller there. And I am just sketching here. So, to finish the box, so I took both of my vectors, I put them tail to tail, I drew my mirror images to finish my box, and that means my resultant goes from that same juncture of tail to tail to my head to head on the other side. And this should give me a pretty good idea about what my answer should look like. So I'm expecting a vector that's a little bit longer than my other two, and something that points right about 90 degrees. So that gives me a way to check my answer, to tell me whether or not I'm even on the right track. So I'll write that down. So I'm expecting something a little bit bigger than an inch, and something kind of towards 90 degrees. But let's go ahead and do the math and see if we can actually prove that. So we're going to take each of these vectors in turn. So I'm going to take vector A and I'm going to pull it apart. I'm going to finish out and make it look like a triangle here. 45 degrees, 1 inch, so there's my vector right there. And I want to know the x component of my vector A and the y component of my vector A. Both of these are A, yeah, yo-yo. Since I have this angle down here on the lower left-hand side, that means this is my x, this is my y, this is my adjacent, this is my opposite, however you want to think about it. So to find my x side, I can use what my knee-jerk reaction is. I can use cosine to find my x side. I'm going to go ahead and rearrange this. I know I'm looking for x, so I'm going to go ahead and get x by itself. To do that, I need to multiply both sides by h. So now my equation looks like that. And let's plug in what we got. Our hypotenuse was 1. Our theta was 45. So my x value is 0.707. To come up with my y component, again, that y is right where it knee-jerk traditionally would be. So I'm going to use sine to find that Once again, I'm looking for y, so I'm going to go ahead and get it by itself. So now it's just a matter of plugging everything in where it goes. Once again, I picked easy numbers on purpose. One other thing I should mention, remember we talked about directions, it being really important to identify directions as positive or negative? I'm going to use the old standby, which means that both my x value and my y value are positive, and they should be positive, and those are the numbers that I got. If I look at vector b, so we're just going to hold off on those for just a minute. Vector b up here, you can use it either way. You can use it as it's written, with the angle with that 45 off of the vertical, or you can switch it and figure out this angle here, if you would prefer something a little more familiar. I'm going to leave it like this just because I can. But look at here. This is now my adjacent side. This is now my opposite side. So the vertical side, the y piece here, it is now the adjacent side. If we go back to our list here, the adjacent side requires cosine. So I'm going to actually be using cosine to find y. How weird is that? I'm looking for the adjacent side, so I'm going to rearrange it. Plug in the numbers we have. And since this is weird, I'm going to make myself a note that that is actually the y of my vector b, because otherwise I will forget. In physics, you'll learn very quickly, label everything, because you will forget. Now I need this opposite side over here. And just as we predicted, I gotta use a weird function. Can you see that? Yes, you can. So hypotenuse times our sine is going to give us our opposite. So that's 1 sine of 45 equals 0.707, but look where it's pointing. It's pointing this way. And if you remember our sign convention, that makes this negative. So my xb is a negative value. So I have pulled my vectors apart. That's the first thing you should always do. Pull your vectors apart. Now that I've got them pulled apart, we can go in and combine them. So I'm going to take my x piece from vector A and add it to my x piece from vector B. So let's see, that's this piece here and this piece here. So 0.707 plus negative 0.707. Would you look at that? The x component of my resultant is 0, which is about what we predicted. No horizontal movement at all. Now let's do the y piece of A plus the y piece of B. It's this guy right here and this guy right here. That's what, 14, carry the 1. A positive number, a little bit longer than the 1 inches we started with. Again, it's about what we expected. So let's take our x piece and our y piece and combine them together. So we have just started completing another triangle. So we found the x piece, we found the y piece. In order to find the hypotenuse, we would have to do Pythagorean theorem. But if you look at this, here's our typical formula. All I did was take Pythagorean theorem, which would have this squared, and went ahead and moved the square root over. That's all I did. We have 0 squared plus 1.414 squared square root. Haha, cancels. That is my resultant. That is my magnitude. We're in inches. All that's left is to calculate the angle. If you wanted to, you could use inverse, tangent, cosine, sine, whatever your little heart desires. Just remember that it is in fact inverse because we are looking for the angle. But since I have a 0 in my x component and a number in my y component, I already know that it's 90 degrees. So I hope that was a little bit clearer than the previous video. Again, I apologize for my rushing through. There will be more examples forthcoming. We'll start dealing with 2 vectors going in completely different directions that don't give you pretty answers like this, all the way through to adding together 3 vectors, 4 vectors even, to see what you get for that final answer. So if you have any questions, any concerns, please feel free to comment below. Otherwise, again, there will be more difficult examples forthcoming, and I will see you then.